Hello and welcome to this crash course on model identification in CFA and SEM. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials, usually related to multivariate methods including factor analysis, structural equation modeling, multi-level modeling, and latent class analysis. If this is something that interests you, please consider subscribing to this channel. Also check out the description for additional resources, including workshops that I teach for QuantFish. In this video, I want to teach you the basics of model identification as they apply to confirmatory factor analysis and structural equation modeling, but also to something like path analysis with observed variables. So let's get started. What is model identification and why is it relevant? When we estimate a factor model or a structural equation model, such as this very simple model here with a single factor and two indicators, there are a number of unknown parameters that we estimate in a model like this, and we need to make sure that we have enough information in our data in order to find a unique mathematical solution for each of those unknown model parameters. So let's take a look at this example here in more detail, and let's see what parameters are in this model and how we can identify those, how we can find the information for a solution, to find a unique solution for those model parameters. First of all, let's take a look at the measurement equations that are implied by a factor model like this. So here we have two observed variables, y1 and y2, and they measure a common factor f. And so in this measurement model, in a typical factor analysis, we have an intercept alpha I, so here alpha 1 and alpha 2 for our two variables. Those are additive constants or intercepts, and we have factor loadings lambda, and then there's a factor obviously in the model, and there's an error variable epsilon also in the model. We call such a factor model a congeneric measurement model. That refers to classical test theory measurement models, where the congeneric model is the least restrictive measurement model of classical test theory, where the variables can differ both in terms of the units of measurement as reflected in the loadings lambda, and also in the origin of measurement as reflected in the additive constant, the intercept alpha. So a congeneric measurement model like this is very common in structural equation modeling. So let's take a look at how a model like this can be identified. And obviously those things are a lot more complicated when you have larger models. Here we have only a single factor model, but when you have an SEM with more variables, more observed, more latent variables, the same principal ideas apply, but they become a whole lot more complicated, which is why I chose the simpler example here to teach you the basics, okay? So next, let's take a look at the list of all model parameters that are to be estimated in this simple factor model. And so even though this is a small model, it already has 7 unknown, or we sometimes say free or freely estimated model parameters. We have the intercepts, alpha 1 and alpha 2. We have the factor loadings, lambda 1 and lambda 2. We have the factor variance, and we have the error variances, variance epsilon 1 and epsilon 2, that we estimate as part of this model. So notice that for the variables in the model f and epsilon, we estimate variance parameters. And so that's already a pretty long list of unknown model parameters for a small model. And now you can imagine that things are a lot more complicated when you have a larger SEM with more indicators and more latent variables. Next, we have to talk about where does the information come from that we can use to find those unknown model parameters. So what is the available information? Where does this come from? Obviously, it comes from our observed data. It can't come from the latent variables because those aren't in our data set. They are part of the model, but we don't have the information directly on the factor variance and the error variance, for example. So we have to draw on our observed variables, y1 and y2. And the first aspect here is with regard to the mean structure of the observed variables. So each observed variable has a mean, and that mean is used in a confirmatory factor analysis or structural equation model to estimate unknown model parameters. Next is the covariance matrix of the observed variables, and that's often the key focus of a CFA and SEM. So we often use covariance, or that we use the term covariance structure analysis for or as a synonym for structural equation modeling, because these models often focus on modeling the observed covariance structure. Now, the covariance matrix contains both the variances of the observed variables and the covariances. The variances you find in the main diagonal of a covariance matrix. So in this case, 7.614 is the variance of y1, and 6.212 is the variance of the second indicator y2. The covariance here is 4.724. With two variables, obviously there's only one covariance. If we had more indicators, then there would be more covariances. So in summary, you can see we have 5 pieces of information here that we can use. In general, you can use this formula to compute the pieces of available information, where M in the formula stands for the total number of observed variables, yi, in this case 2. So here we have 2 times 2 plus 1 divided by 2 plus 2 equals 5 pieces of information. In this formula, the fraction gives you the available information that comes from the covariance matrix, and then plus M after the fraction refers to the M means that we have with M variables. So this formula is practical when you have a larger number of observed variables and you don't want to count all those pieces of information by hand. Now, back to our model, we can now look at the relationship between the parameters that we want to estimate and the pieces of information that we just calculated, and that is often done in the calculation of the degrees of freedom. The degrees of freedom are given as the number of pieces of information minus the number of free model parameters. In our example, we saw we have 5 pieces of information and we have 7 free model parameters, so our degrees of freedom are -2. And that is something that is not good. So that already tells us this model is under-identified. It cannot be identified, or those parameters, those 7 parameters, cannot all be identified. We don't have enough information. So this is one very fundamental aspect of model identification, that you have to have greater than or equal to 0 degrees of freedom in order to identify a model. So this is a necessary condition. It's not sufficient to have 0 or positive degrees of freedom, because models could still be under-identified even with 0 or positive degrees of freedom. But at least you know when you have the case of negative degrees of freedom like here, then you know this model cannot be identified as a whole. So what can we do about this? So obviously, when you have only 2 indicators, you have very little information. You have only the 2 means, the 2 variances, and the covariance. That's not very much information, so you can't estimate a whole lot of parameters. So there are essentially 2 ways in which you can make this situation better. One is you can add more variables. With more variables, you would have a larger covariance matrix, and then you would have more pieces of information. So let's say if we had a 3rd variable, then we would already have 3 means, 3 variances, and 3 covariances. So we would have 9 pieces of information. So that would be better. Or you could have additional variables otherwise in the model, so as predictors of the factor, for example. So you could add in more information in terms of more variables, either by having more indicators or by having other factors or other variables that are related to your factor here in this model. Now, if this is not possible, let's say you only have those 2 variables, so you cannot get more information by adding variables. In that case, you have to reduce the number of unknown parameters. That's your only option in that case. So you have to take something away. And so then the question is there a reasonable way to take something away from the list of unknowns to bring that list down to where we have enough information to estimate the remaining parameters? And so In our case, one reasonable assumption may be that the two variables have equal loadings. And so we call that a model of tau equivalence or essential tau equivalence if we retain those different intercepts in the model. And so that's also a model of classical test theory, the model of tau equivalence or essential tau equivalence. And so that applies when your variables are measured in the same units of measurement. So when you have variables that come on the same scale, so let's say, for example, parallel tests that have the same number of items and are otherwise also comparable, then it may be reasonable to assume that the factor loadings or item discrimination parameters are equal. And so in that case, we may be okay fixing them both to 1, which implies that they're equal. So in that case, when we can do that, when we can assume essential tau equivalence, then our measurement equations simplify, because then the factor loadings lambda get dropped. They are no longer unknowns in the model. And in that case, we have only 5 unknown model parameters left, namely the 2 intercepts, the factor variance, and the 2 error variances that are still being estimated. Now, in that situation, obviously the degrees of freedom are 0, because now we have 5 parameters left and we still have 5 pieces of information. That hasn't changed. And so 5 minus 5 is 0. So this model could be identified. We say it could be just identified because there's just enough information potentially to estimate those 5 unknown model parameters. However, we still have to show that it's possible, because having the same or more pieces of information than we have, as we have model parameters, is only a necessary but not a sufficient condition for model identification. So we still have to show that with our 5 pieces of information, we can find unique solutions for those 5 model parameters that are remaining. So let's take a look at how that works. How do we show that? And we're going to begin with the intercepts or additive constants here. Remember, here are our measurement equations. Again, each variable is equal to an intercept alpha plus the factor plus the error term. And now what we can do is we can take the mean of the sum on the right hand side of each equation. So E here is the expected value or mean. And so when we take the mean of alpha plus factor plus error term, then all that remains is alpha, because the mean of alpha is equal to alpha, so it's the mean of a constant, and the mean of the factor is assumed to be 0 in this model. So the factor is centered, that's the default setting with most cross-sectional structural equation models and factor models, that we don't include a mean for the latent variables. And then also the mean of the error term epsilon is 0 by definition, because errors of measurement average out. So in classical test theory, by definition, the error term has a mean of 0. And so that shows you that the identification of the intercepts is straightforward, because they're simply equal in this model to the observed variable means. So that's pretty trivial in a way. So those intercepts are not terribly interesting because they simply reflect the observed variable means. Next, let's take a look at how, if and how, we can identify the factor variance. And again, we're going to take our measurement equations here, and now we're going to consider the covariance of y1 and y2. And so when we take the covariance of y1 and y2, then that's equal to the covariance of the first sum with the covariance of the second sum. And that can be solved according to rules of covariance algebra. And when we solve that, then it turns out that all that remains is the covariance of the factor with itself. And that's because the constant alpha does not covary with any term, neither with itself, nor with the factor, nor with the error term. So all those terms where the constant here covaries with something else, they're all 0, because constants by definition do not have a covariance with anything else. So alpha drops from the model. And then F by definition is uncorrelated or does not covary with the error term. in the model. So those covariances between f and epsilon also drop from the equation, and epsilon 1 is not correlated by definition, or at least in this model, with epsilon 2. So the error terms are uncorrelated as well here. That is an assumption of this model. And therefore, all that remains is at the end the covariance of f with f when you apply rules of covariance algebra to this term here at the top. And that can be further simplified because the covariance of a variable with itself is equal to the variance of that variable. So covariance of the factor with itself simplifies to the variance of f. So that shows us that the factor variance is identified in this model in terms of the covariance between y1 and y2. And that's less trivial than what we saw for the intercepts, because that's something that may not be obvious to us, that the covariance of tau equivalent, or essentially tau equivalent variables, identifies the latent factor variance. Next are the error variances. How are those? Are those identifiable, and how are they identifiable? Again, here are our measurement equations, and now we're going to take a look at the variances of those two sums. So when we take the variance of alpha 1 plus f plus epsilon 1, which is in the first equation here, then that simplifies to the variance of f plus the variance of epsilon 1. And that's because a constant has no variance. So variance alpha 1 is 0. That drops from the equation. And then also there's no covariance between f and epsilon 1. Therefore, we don't have to add a covariance to this variance decomposition. It's simply additive. And the same applies to y2 as well. So we get an equivalent equation here for the second variable as well. So in this model, the observed variance of a given variable is broken down additively into factor variance plus error variance. And that's again in line with what we do in classical test theory also. And then we can now insert what we already have for variance of f, because from the previous slide we know that the variance of f is identified via the covariance of y1 and y2, and we can apply that here. So we can replace var f in both equations with covariance y1, y2, and then we can solve the equations for epsilon, which then gives us variance epsilon 1 is equal to variance y1 minus covariance y1, y2 for the first variable, and for the second variable we have the variance of the second variable minus the same covariance. So that's pretty straightforward, and that shows us that the error variances now are also identifiable in this model. So we've shown that for the two intercepts we have a unique solution, meaning they are directly linked to observed information. The factor variance was directly linked to the observed covariance, and the error variances are directly linked to the observed variances and the covariance. And so the key point of model identification is that you can show that on the right-hand side of these equations, you only have observable information. So on the right-hand side, you have to have only things that you have in your data, meaning means, variances, and or covariances of the observed variables. If you can show that for each and every model parameter, then your model is identified. And here we have shown this for this model. Again, this model is just identified, or we say saturated. It has 0 degrees of freedom because we used up all 5 pieces of information that we have in our data to estimate those 5 model parameters, and nothing is left over. This means that this model can be estimated, the parameters can be estimated. However, the model fit will not be informative, or the fit will be perfect trivially. There will be no chi-square value that will allow you to test the model, because the model has 0 degrees of freedom, and so it must fit perfectly. By definition, the only way that this model could be falsified could be if the variables were not correlated. So if the covariance was 0, then obviously the variance of the factor would be 0, and then that means the model doesn't make sense. Also, when you have a negative covariance between the variables, that would also be strange. Now, this could be a coding issue, but in general, you would expect a positive covariance for tau equivalent or essentially tau equivalent variables. And so that should also be something that you should see in the data, that the covariance of y1 and y2 is positive. If it's not, then that would speak against the validity of this model. Now, how could you obtain an over-identified model? In this situation here, you would have to include additional restrictions. So you could, for example, make an additional assumption regarding the error variances, and you could assume that the variables have equal error variances. Then you have a model of essentially parallel variables in the sense of classical test theory, and those variables then would have equal reliabilities as an implication, and that would then result in a testable restriction if you set the two error variances equal, variance epsilon 1 and variance epsilon 2. In that case, you would need only one of the two equations here at the bottom to find the common error variance, because if those are equal, then one equation is sufficient to find that parameter. And so that would then have the implication of equal variances for the observed variables, and that would be a testable restriction. So you would then have 1 degree of freedom because you're estimating the error variance only once. And so then you have only 4 parameters, but you still have 5 pieces of information. And so in that situation, your model would be over-identified with 1 degree of freedom, and you could test whether the variances of the observed variables are equal in the population. I hope you found this video useful to learn about model identification in confirmatory factor analysis and structural equation modeling. If you did, then please subscribe to this channel and don't forget to check out the description for additional resources, and I'll see you next time.